Marine Technology Lab, Stage 6, Semester 1 Video Presentation by Nathaniel Campbell-Scott-Howells. 2019 Stage 5 cohort identified a need to connect the centralised Union Street urban development with the harbour side and the beachfront. Right now, the site is heavily industrial and scattered. There is, however, a large potential for redevelopment as some of the functions and area may move to the new harbour on the other side of the river. During Stage 5, I chose to develop the vague Research Lab, choosing to interpret the functionality in line with developing renewable energy generation and engineering-focused prototyping in a manufacturing facility. Partnering with a group like EMEC, the European Marine Energy Centre, to offer local services to small independent teams and companies to realise and test their wave and tidal energy solutions. Aberdeen is convenient for this, being relatively close to their current Orkney testing site and possessing strong transport links and industrial connections. This will be about connecting Aberdeen's past with the future of Scotland, easing some of the difficulties found in its transition from an oil-based economy. Scotland is fast approaching complete independence from fossil fuels within the national grid, and there are plenty of opportunities to explore our experience to the rest of the world. Architecturally, I would like to explore the relationship between the sea, the organic textures, and the aesthetic of sustainable timber, and how that interacts with the defined skyline of Aberdeen. Whichever solution I develop, due to the brief, it would be one of the largest buildings on the harbour front. By establishing a firm presence on the harbour quayside, it becomes easy to see how it integrates into the urban fabric. With easy access for both cars and boats, I have placed the building in a manner which allows the quayside to be extended, taking into account the variety of cargo ships' lengths. Similar volumes could then occupy the area north of the site, with residential on the northwestern edge. Once I had established a 3-bay solution in Stage 5, it was obvious that a thin plan strategy would be unsuitable for the shape of the site, so a thick plan is the only logical approach from here. The largest spaces are in the middle. Circulation would then go either around the outside edge, or as I desired to keep a more self-contained outlook, on the inner edge of the smaller bays. This would also make it easier to incorporate functions such as a draft lobby into the design without compromising any structural or substructural grids I establish. With the primary entrance on the eastern edge of the building, a division across the length of 2 bays allows for the separation of public and private functions, with the added benefit of increased safety as the warehouse area could have heavy machinery operate within it, and the workshops dangerous tools. The void space created on the eastern edge would then be able to be used as parking spaces or charging points for electric vehicles without intruding on the rest of the area. The first floor matches the circulation floor of the ground and switches out the external facing workshop spaces for flexible offices. It is with the full building schedule that the covered dock area makes its largest impression as far as scale is concerned, taking up around 1,500 square metres of floor area and encompassing volume across the full 2 double height stories of the scheme. I have positioned 8 fire escape routes within the building. With this, occupants are never more than 25 metres away from an alternative exit if the one they are closest to proves unsafe. On the east elevation, there are no vertical window openings, with the primary feature being the recessed bay-deep visible division of the 3-bay system. The draft lobby occupies the lower left side, as a subtle, unobtrusive way to maintain as much environmental integrity as possible without compromising the interior plan of the building. It is this approach which will allow users to appreciate the distinct profile 4 large sawtooth skylights that span the length of the building to bring light into the thick plan. The south elevation has the most prominent display of the roofing sheet material, recycled aluminium corrugate, helping to reinforce the industrial nature of the building. The door openings on this edge are for fire escape only, with vehicular traffic passing by to access the pier. The west elevation has the largest openings to accommodate a covered dock area on the left, a fire escape with boat access in the middle, a van-appropriate loading dock, and another human fire escape on the right. The corners of the building would be partially recessed envelope in order to accommodate a timber-clad drain pipe on each one. The louver system present over the window openings aims to serve 2 functions. It allows for greater control of lighting conditions on the north and south facades, and aesthetically brings the window openings into alignment with the horizontal-oriented cladding. These stay above the door level in order to create a hierarchy and reduce the monolithic effect when walking directly next to the building. During the semester, exploring how to execute steam strategy structurally was important. While I had roughly worked out a system and plan, I had to tie it in with a coherent roof strategy. Vitso, a furniture design company, partnered with Wall Thistleton to create a laminated veneer lumber structure to house their headquarters. They established a rigorous structure to envelope solution, with 7.5 meter bays and 600mm deep beams, only possible because of LVL. It had a high cost expense. Natural light is prioritized through the use of large 40-degree angled north-facing skylights. Servicing through the building is exposed, with the glulam columns featuring grooves cut out of them for cabling. I visited Tesco Bankery by Manson Architects, which they tout as generating 87% lower embodied carbon than comparable steel constructions. They achieved 21 by 12 meter spans through the use of glue laminated timber and large Y columns. The lab structural grid features two modules. The smaller rings are a series of 11 by 11 meter boxes, and the span between them is 34 by 11 meters. I made accommodation for movement joints in the solution, with the three bays being structurally independent from one another. I then had to determine how to connect the beams and columns together, and how this would express itself to the occupants of the building. Tension cable bracing would be present along the roof of the small bays, and on their gable ends. The large spanning middle bays would use portal frame-esque triangular bracing in asymmetric arrangement. Structural glulam can be shipped directly from Perth, lowering carbon emissions from the transport of materials. Some form of strong connection is required. I chose to use hidden metal plates as a rigid connection. Only the bolts securing the whole assembly would be seen from the outside. Wooden columns of any form are unable to be connected directly to foundations due to capillary action. Metal plates are fixed to the bottom of the column and then secured to the concrete feet of the pad foundation. Developing the primary section of the building has been difficult, determining the most optimized skylight arrangement, the proportions of the two stories within the wings in relation to the larger warehouse space, and how this connects to the overall strategy have been deceptively complicated procedures. By interim 2, I had managed to determine that the workshops and office spaces could be primarily daylit from the edges of the envelope, leaving the defined sawtooth skylight system in the middle. The final solution resolves itself with 4 teeth running along the length of the scheme. This amounts to 25% of the roof surface area being dedicated to skylights, which has been shown to be roughly the sweet spot for carbon emission savings and cost in relation to potential thermal cooling requirements. The covered dock area is thermally isolated from the rest of the structure, with the envelope being sandwiched between the two sets of columns on either side. This also maintains a visual connection. Here it is easier to see how the service voids are incorporated into the section and how the external cladding system relates. Section BB cuts in the opposite direction to AA through one of the stair cores. From the first floor circulation bridge, it's possible to look down the warehouse and through to the activity on the covered dock area. Cutting through the corridor, the stick-based glazing system can be seen here, allowing uninterrupted views across the dock space. Net zero is as much about offsetting carbon emissions as it is about minimising. In an industrial building, though, there are limits as to what can be cut. When mapped against the UN Sustainable Development Goals, the building has been designed in the spirit of them. The north-facing skylights should provide a consistent and reliable daylighting experience throughout the day. I've been exploring how to achieve this since stage 5 and ended up with the 4 rows of skylights. Any artificial lighting solution for a large space like the warehouse would probably have to be hung from the primary structural roof beams. The main circulatory and occupancy zones would be heated with underfloor heating. This would then be complemented by radiators in the warehouse, and the envelope could be sealed from the covered dock area. Passive ventilation would use vents in the external envelope and possibly make skylights openable. The heating solutions for the building should treat the middle bay as both a buffer and potential heat store, given the primary function of this area is either circulatory or warehousing functions. Heating this space mechanically is redundant, especially with potential for temporary mass heat loss via the docks area. The sawtooth skylights would use a fiberglass and polyurethane frame for lower view values than conventional aluminium ones. These could be automated to open when the building requires cooling, and a roller blind could be fitted underneath them to prevent excess thermal gains. The louvers could also be automated to control thermal gains. When the primary loading bay is sealed, it is unlikely to create much interference, but when it is left open, increased interior humidity during the day and warmer temperatures at night should be expected. Where heating solutions are required, underfloor heating makes the most sense as far as efficiency is concerned. Due to the movement of heavy machinery in the primary warehouse space, creating an underfloor heating system there could have issues due to vibrations and strong impact forces. A wall-mounted radiator system there could resolve that issue. Acoustics have been one area of the design development I unfortunately have neglected somewhat during this project. It is possible to draw some conclusions. With the large warehouse area being uncontained, it is likely that the rest of the circulation area will experience some of the noise from that area. Due to the tall ceiling and suspended floors, though, the first floor should be mechanically isolated in their office spaces. The corridors could be lined with a wood-based dampening system, but I have not explored this. Beyond general factors, choosing a location for plant room, general heating, ventilation approaches, and making a service void in my section detail, I have not fully considered the servicing regimen fully. The cladding and opening system follows the structure and expands into a tartan grid. This is assembled in the form of a timber cavity wall with cross bands to support the variations in cladding. Here you can see a skylight detail and the way the envelope is sealed and the service void is sitting in the middle there. And here is the detail that it looks at the floor junction and the suspended floor. Inside the warehouse, the covered dock area. This is probably one of the most important views. A workshop, offices, circulatory corridor outside reception. Exploring the relationship between the water and the harbour front, the organic textures of timber, and the defined skyline that forms a core part of Aberdeen's identity. Using modern timber technology to create a flexible and legible variety of interior spaces to facilitate the functions of manufacturing process machine components. Establishing a new warehouse typology that can be adapted across the harbour. Emphasising access to natural daylight, human-scale interventions in a monolithic and private infrastructure. The Marine Technology Lab. Thank you for your time.